All right, let's talk about something you've probably seen, maybe even taken 1,000 times, but never really thought about: the humble pill. I mean, it looks so simple, right? But making one and making it perfectly, well, that's an incredible scientific challenge.
Seriously, have you ever wondered how it's possible? How every single one of those little tablets in a bottle has the exact same dose, the same weight, pretty much the same everything? It's not magic, I promise you. It's actually a pretty amazing feat of engineering. And the whole secret, the key to it all, comes down to taming just one thing. Let's call it the main character, or maybe the main villain of our story today, the stubborn powder. Yeah, just getting this fine, dusty stuff to behave, that's the entire game.
So, Section 1, the stubborn powder problem. Okay, so what's the big deal with powder anyway? Well, it all boils down to one word: flow. If you can't get that powder to move smoothly and predictably, you just can't make a safe pill. It's really that simple.
And this is where things get really serious, because if that powder clumps up or flows unevenly into the machine, well, one pill might get too much of the medicine and the next one might get too little. And that's not just a quality issue, that is a huge, huge risk to patient safety. Okay, to really get what we mean by flow, think about one of those sugar dispensers at a diner, you know? When it gets all clogged up with moisture, you shake it, nothing happens, and then bam! A giant clump just ruins your coffee. That's poor flow. Now picture pouring fine, dry sand from a bucket. It's smooth, it's consistent, it's totally predictable. In the world of making medicine, getting that perfect sandy pour is, well, it's everything. All right, Section 2, diagnosing bad flow. So how do scientists actually play detective with this stuff? I mean, they can't just look at a pile of powder and know if it's good or bad. No, they have to measure it, and they use a very specific set of tests. What they're measuring is a property called flowability. It's the official term for how well a powder moves under all the conditions inside the manufacturing equipment. Gravity, pressure, you name it. You can think of it like taking the powder's pulse. It's the key vital sign for its health. And to measure this vital sign, scientists rely on a gold standard of 3 crucial tests. These numbers, these 3 little data points, tell them absolutely everything they need to know before that powder can move on to the next stage. First up, we've got something called the angle of repose. Just imagine pouring the powder onto a flat surface. It's going to form a little cone, right? Well, the angle of that cone's slope needs to be less than 30 degrees. If it's any steeper, that's a huge red flag. It means there's too much friction between the particles and they're sticking together instead of flowing freely. Next on the list is Carr's index. This test basically measures how much the powder compresses. For great flow, you want this number to be under 20%. This tells the scientists that the powder has just the right density. It's not too fluffy and not too packed, so it can perfectly fill the little mold for the tablet every single time. And the third critical number is the Hausner ratio. Now, this is really just another way of looking at that same density question. It's like a quick double check to make sure Carr's index is on the right track. And the magic number you're looking for here, it's got to be below 1.25. And this chart just lays it all out perfectly. You can see the clear good to go zone and the uh-oh stop zone. If a powder's test results land in that poor flow column, it's basically sent straight to the powder hospital. It has to get fixed before it ever gets close to being made into a tablet. Okay, Section 3, the Flow Improvement Toolkit. So, what actually happens when a powder fails its tests? You don't just toss it out. No way. Scientists have this whole toolkit of tricks to turn a stubborn, clumpy powder into a beautifully free-flowing one. One of the most basic tricks is just changing the shape of the particles. Think about it this way. Trying to pour a bucket full of jagged rocks is a pain, right? They interlock, they get stuck. But pouring a bucket of marbles? Super easy. They just roll right past each other. It's the exact same principle here, just on a microscopic scale. Now, this whole process of changing particle shape and size has a name: granulation. There are a few ways to do it. With wet granulation, they use a liquid to kind of glue the fine dust into bigger clumps. With dry granulation, they just use a ton of pressure. But honestly, the most elegant method is spray drying. This creates these almost perfect, tiny little spheres that flow almost like a liquid. But it's not just about reshaping things. Scientists also add a few special ingredients to the mix. You've got glidants, which act like billions of tiny, microscopic ball bearings. They just cut down the friction so particles slide right past each other. Then you have binders, which are like a gentle glue to help those granules form and hold their shape. And finally, fillers are added to bulk things up, which helps with both the flow and the final step of pressing it all into a solid tablet. Okay, part 4, the rules of perfect flow. So we fix the powder. It's flowing perfectly. We're done, right? Ha, not even close. Now comes the hard part. You have to maintain that perfection. And for that, you need some very strict rules. This is where the Standard Operating Procedure, or SOP, comes into play. This is the official rulebook. You are constantly retesting the powder using those same metrics we talked about. You're ready to make tiny adjustments on the fly if you need to. You control the environment like a hawk. Humidity and temperature have to be absolutely perfect, and you write down everything. It's a non-stop cycle of quality control.
Moving on to Section 5, risks and controls. Because even with this amazing toolkit and all these strict rules, things can still go wrong. Every single solution we've talked about has its own set of risks that you have to manage very, very carefully. Remember those microscopic ball bearings, the glidants? Yeah, they're fantastic for flow, but if you add just a little too much, the final pill might end up being too soft, or worse, it might not dissolve properly in the body. It is a super delicate balancing act. And how about those fines, those really tiny dust-like particles? Even in a perfectly granulated batch, you're always going to have some left over. And if you have too many, they can actually separate from the bigger granules while everything's moving around. And that brings you right back to square one, the risk of inconsistent doses. In that environmental control we were so fanatical about, it's not just about flow. If the humidity in the room creeps up, that powder can start clumping all over again, undoing all that hard work. And even worse, it creates a perfect environment for microbial growth. Yikes. So what's the bottom line here? The ultimate answer to all of these risks is just constant, obsessive control. You have to be monitoring the process at every single step and maintaining that perfect environment. There are absolutely no shortcuts. So you see, that journey from a stubborn, clumpy powder to a perfect, uniform tablet, it's a story of incredible science and precision engineering. So the next time you see a simple little pill, will you still think it's so simple? It really makes you wonder, right? What other simple things in our lives are hiding this much complexity?